So this will be a bit maybe different presentation. As Eric said, we'll just show some of the structure of the project, but then I want to go really in the details of what we have produced and achieved. So as Sassan, Henrik already said, we will start with the Aalto prototype, then Acrio and Lund University FSO, and live testbed from Turin, if the LAN connection works. Before we start, just to say that this project came with quite a lot of partners and nice collaboration. So in Stockholm we had Ericsson, KTH, Acrio and Lund University, then Aalto in Helsinki node, and in Turin we have Telecom Italia and Cappetti Elettronica, which is an SME collaborating with Telecom Italia. The project has three main topics. The energy efficient networking, that is kind of continuation of the 5 Green project that Eric mentioned there, and Dario is the technical leader for that task. Then we have the transport, that somehow it's a continuation of the architecture and features proposed in the other transport project that Eric mentioned as well. And here we have Per, technical driver, Anders, I see also Paolo there, and Pernil and so on, Khan. And the last one is M2M and IoT. It's a kind of continuation of the M2M RISE project that we were having last year, and Sassan is the technical driver of that task. The nice things of this project is that finally we could have a kind of a holistic view of these three main topics, because we saw that before when you have a project focused on just one things, you tend to try to solve that specific problem and probably generate problems somewhere else. I mean, we saw, for example, for the M2M sensors, an idea to reach when they are in basement is to, for example, send the same signal 1,000 times to accumulate enough energy so that the sensor could decode the signal, which is good as that specific problem. But what about the energy saving part? So it was really good to have this big project, even it was so difficult to manage it. But I think we could have like a different approach to problem. When it comes to M2M, for example, we tend to divide the M2M world in two main groups. On the left side, you see what we call a massive M2M, where there are kind of sensor with requirements like that has to be cheap, as we said before. We saw it from Telefonica IoT presentation, and but there are a lot of them. The revenue coming from each of them is very low, so you need to go in very, let's say, zero cost of managing them. On the other side, you have the mission critical M2M, which is something with the completely different requirements, like in terms of reliability and so on. And that is probably going in the direction of the 5G network. The current network probably is not always able to offer that kind of service with those strict requirements. But we saw that all in all, there are some kind of horizontal problem when it comes to the resource management of those devices, and how, for example, you do the random access and so on. And also in both, you need some kind of architecture enhancement to cope with this new kind of problem. And we have looked into that. Also, for example, we propose the capillary network concept, where you can have the cellular network used as a backhaul, and then the last hop to reach the device, you will use different technologies. You can have like Bluetooth low energy, Wi-Fi low energy, and so on. And now this capillary gateway is to be integrated in the cellular network. Can be different depending on the application you are doing it. So we have proposed different solutions for that. When it comes to energy savings, Dario will tell us more about that, but just to give you an example, that in the standard they are discussing how you can put, for example, the device on sleep, and then the problem is that you cannot reach that device. So on the other hand, when you need to keep the device in the system to understand where it is and when you can send the signal in which cell is the device is to be reachable. So also there is quite a lot of work done in find the right trade-off between how much the device can sleep, what we call it the DRX mode, and how often the device should be reachable and so on. Then we also looked at the transport architecture, and Per and Anders will tell us more about that. But also here, there are different solutions we propose depending on the use case. Here, for example, we saw that, I mean, of course, everybody would like to have optic fiber at home, but it's extremely expensive, and sometimes the operator don't see how can they come back in revenue with the cost they would have to drill the optic fiber until your apartment. So here we can say that there are solutions we propose, kind of cheap solution that you can have quality enough for what you need without using optic fiber. But again, Anders and Per will tell us more. So just to show a little bit of us, here it's in Turin, it's the live testbed. You see there is a capillary gateway in the middle, and Dario will show us. There is Turin connected to us in a few minutes. And we have been also quite active in publication and in dissemination events. For example, we have been even in Hong Kong. Sassan was the chairman of the workshop we organized there, and here is a picture of us. We were like also, of course, advertising IoT digital there, and I think it was a really nice experience. We also have been in Expo. Here again is Dario talking about energy efficiency there, and so on. I mean, quite a lot of work has been done, but I think what is more fun for you to see, if Sassan can come, is we start with the real stuff we have done. Thanks.
Okay, good morning everybody. My name is Sassan Iraji. Thank you, Francesco, and I'm here representing Aalto University together with my colleague, Hussein Ali. And today we have actually two good things here to share with you. First is the video for the prototype. We actually call it prototype. It's not a demo because you will see it and then you see after that what is the result of that prototype. So we start with that. We try to make it self-contained, so there's my voice there. If it's not that loud or something wrong with that, we did it at university with just a small camera. But we put a lot of effort. I tell you, 20 hours maybe or so. So let's see how it's come. At Aalto University, Department of Communications and Networking, we have designed and implemented a prototype for low-power remote device-free intruder localization system based on radiotomographic imaging. With this system, one could localize precisely an object within an environment without using any tags attached to it. For our experiment, we used a small lightweight robot called Pioneer 3DX, which is ideal for indoor use. The Pioneer 3DX platform has ability to localize using sonar, laser, and onboard inertial sensors. Robot can be controlled by an operator, or it can navigate by itself. In order to use the robot in our experiment, we installed a barrel on top of it filled with the liquid which represents the electromagnetic properties of human body at 2.4 GHz frequency. This figure shows our system overview. As it is seen, we are deploying a low-power capillary network based on IEEE 802.15.4 radio. The low-power capillary network will be managed by a gateway node, which can be remotely accessed over any communication means such as LTE system. The intruder is our robot. The network data will be relayed to operator through the application server. The operator is a remote off-the-shelf laptop computer which is running one of the popular operating systems such as Windows, Linux, or Mac OS. The operator gets the collected measurements in time-critical manner and is able to configure the system. The intruder position is estimated using radio-received signal strength measurements of each node in the capillary network. We demonstrate the system in 4 stages, 2 of which are required for preparation. First, we deploy the system and set up the stage for the experiment. Second, we run the robot around the stage to collect the data from its laser scanner to create the map of the environment. After that, we use our own developed software to fine-tune the map. The third step is to do the actual experiment where we do the localization, and finally we generate the results. In this stage, you see the environment created by the experiment. The network is accessed by the operator using a sync node. The capillary network of 16 nodes is deployed in a rectangular area of approximately 6 by 6 meters. The robot is also equipped with a node to synchronize its position measurements with the capillary network operation. The obstacles are chairs and tables in different positions, and the nodes are adjusted on tripods approximately 1 meter above the ground. Map creation includes 3 parts. First, we run the robot to collect the data from its laser scanner. Second, the distance measurements from the laser scanner are registered to create a map of the environment. We observe the collected data and the robot movements in a graphical form. Finally, we process the map data by grouping the points to make a cleaner map for the real experiment. This allows easier node position assessment and visual evaluation. In this stage, we experiment the intrusion monitoring. The robot wanders randomly on the stage. When it senses an obstacle, it changes the direction. Sync node generates beacon signal periodically, and the other nodes transmit their measurements using frequency hopping in 3 channels in round-robin fashion. The node's transmissions are sniffed by the sync node, and the measurements are acquired for real-time intruder localization using radio tomographic imaging. In this graphical presentation, the localization results of both radiotomographic imaging and robot sensory are shown. As it can be observed, the 2 results are coinciding very closely. This demonstrates the high precision of our prototype design and implementation. Thank you very much for watching our video. Aalto University, Department of Communication and Networking. All right. Thanks. This is all about our prototype. So as you see, we actually deployed really everything implemented, software and hardware by Aalto University. So they are capillary network. They're connected to LTE network, and there are a bunch of softwares. Like I was asking Hussein how many lines of code for even those part of it, and he was saying that don't ask me, it's more than 300,000 or so. So with that one, we come to this that Alberto today was talking about, and this is something that Henrik wanted me to announce also on the stage, because also EIT involved with this, and it's about Internet of Things. And you know that there are these smart things that can be connected. You know, you can have active tagging or something that is connected, but there are something that is not smart. And what do you want to do with those? You want to make them smart or not by adding tagging or something? And if you want to do that, then how you are going to do it? How you are making so modular and like well connected to each other? So with that, we come to this, that in order to make this one, we need some kind of adaptive gateway. It's actually the question I asked to Alberto, that how you can make this thing scalable from the business perspective and from the technology perspective. And you see that in the market today, many people who want to develop this thing, they use Raspberry, or they use some niche for some verticals, that what we have observed. So the question is that how you make this one modular and configurable and scalable. And with this one, we came to this idea with all these things that we have done over the years, and also here is EIT Digital is part of it, and we want to thank you, to this kind of idea of having the building blocks that is configurable and can be deployable easily with what we call as a zero effort. And with this one, we have our startup established with all this activity that we have done over the years, and we are really delighted for this. We're really eager to make this one happen. We already started with a few potential customers. They show interest, they show some of our things, and by the way, we have this thing commercialized already out of EU, and this is some kind of activity we want to do it within EU and then scale it up. So this called Click Technology Limited, and it's kind of a spin-off of Aalto University. And as you can see here, that these blocks are kind of configurable. They can be joined together, or you can use it in different parts very easily. And the good thing is that we are using as much open source so that everybody can have a stake out of it. And then these blocks can be moved for different application, for people flow, or you can do some kind of sensory activity with really zero effort with that. And everything is hidden in the abstraction layer that we are creating in this middle part, which is gateway. So that's about it. And this is something about our website is heavily under construction. It's just 2 weeks registered already. So we have this website. We put some material there, but it's evolving by the time. And we are 3 guys who established this one. I myself as the chairman of the board. Hussein is the, I don't know what you call it, CTO or whatever. And then Professor Riku Yanti, who is the head of our department also, he's part of this one. Thank you. I think I hand over to.
Thanks a lot, Sassan. It's great to see that in the end also we get a startup among all the other things. And by this we can continue to the Per and Anders will show us other practical things.
So we need 2, right? So we have been working with 2, let's not call them product proposals because this is sensitive. Let's call them concept studies. And we'll show you the context. So you hold them. I have to open this. So this is an Ericsson product. It was invented 100 meters that way 2 years ago. This is called the radio dot system. It is the world's smallest macro base station. Well, actually, this is a third of it. So this is the radio head. And we have made 2 concept studies trying to improve this. One is what you saw Francesco show with bringing it into the home, etc. The other that will be on demo tomorrow using FreeSpace Opto, is intended for events. Something like this. Say that there is bad coverage and then we want to temporarily install. But first we'll demonstrate how this is installed today. Okay, first Henrik, we need an Ericsson guy that can act as the indoor radio unit, which is 1/3. This is the indoor radio unit. You're over there. Yes. and you hold this just for now. So you're going to communicate with that. Okay. And we're going to do the installation. Okay, you take one end, find out where. And Ericsson has trained staff to do this, and we have a professor from Lund and a paper shuffling manager from Acreo, so what could go wrong? So I take this one, and then you roll out a lot of that. So this one goes into the indoor radio unit. That would be you.
Yes.
You hold that.
I hold that.
I'll take this. No, that will you in turn will communicate with the baseband unit, which is further up. He has an optical link to him, and then it goes to. We only have 10 minutes, and speed up. So normally this is installed by trained professionals, typically in an enterprise situation. And if you do this in an office, run around over there and come back. This has a 200-meter range normally. We will not, when we replace this, we will have 100 or so until he gets his shit going, but then we'll have 200. So if you install this in an office, this is okay. Also, it will be faster than what he's doing now, because it will be there for 10 years or so. So that's okay. If this isn't, Anders, speed up. Can't you just, run? Olof, could you help him a bit? Because he's not doing very well. He's not a trained professional. But this is how it's done. It's important to understand the reality. And this is it's an indoor thing. This will give indoor coverage once he comes back. However, if you want to do this in a sports event or something temporary, some outdoor thing, you can't. This is not very practical, especially as he has to roll this up when we disassemble the event. So we have thought of a different technology. Acreo are experts in what they call FreeSpace Opto. So you have a laser replacing this. Also, you may think, because this is an Ethernet cable, that this is digital. But digital, Anders, come down here. Will be. You're on your way. I thought you could do it here in the middle. This is not backhaul. This is fronthaul. We don't send digital data over this. We send analog. This is a very big difference. For instance, if we replace this with a laser sending digital data, that has been done. You have gigabits over FreeSpace Opto, but you don't have analog signaling. So run that way. And we will complete the installation. We have an 146-meter cable, but we will not roll out all of it. Yeah. So this is the normal installation procedure, and then it's very simple. If you reach the wall, this will sit on a wall up there, and we will have full 4G and 3G coverage, and life will be wonderful. We'll be included in the information society, etc. However, if this would be an event, then we would need to deinstall this. If you roll it back up. Or we can do that at the end. Okay, where do you have your... I have my part over here. We are going to replace this cable. So I'll be over here. You go to the IRU. So I will use a screwdriver and put this. First I remove the lid. And I will put this. Okay, this is a mock-up, so it falls apart. That one is expensive, so I hope it doesn't drop. I will put this here. This thing will rotate and have a laser, and it will aim. Oh, you have to put it up, Anders, next to the IRU. Yes. You will see this tomorrow. This is the demo that we will show tomorrow. We will have real lasers and stuff, but not with the plastics. So I will put it there. This will aim automatically and find him, and go into sync and have a frontal link. So we will analog data over this. And underneath this, you have the dot. They are mounted like this. And the IRU will then be able to communicate with 8. So there will be a stack of those lasers aiming at different. We wouldn't need 8 in here, but if it's a sports arena, you know, 2 or whatever, Ericsson Globen, you would need many. So that's what we're going to demo tomorrow. You will see the laser part. Do you want to, you deliver a 100 meter. With the cable I can deliver 200 meter, but you say it's 100 meter today. Care to comment?
I think you will get 200. What I mean, I can say that what we started was a digital link, 1 gig, 100 or up to 200 meters. So the project is about adapting this link to the dot system, and that involves analog parts, and it involves the mechanical design to fit things onto the dot. And the reconstruction, I mean, we didn't realize this in the beginning of the project, how much you needed to reconstruct the optical parts too, but there are substantial reconstructions needed. So this is ongoing at the moment. It's not a ready product yet.
It's solved though. All the
solved, yes. I mean, yeah, and we have made a proof of concept, a demonstration. So we have transmitted LTE signal over the free space optical link. But not made it into a product yet. That's underway. So please come tomorrow and have a look and talk to Evgeny and to Jan, the chief scientists behind the ideas.
So imagine now that the event is over and we're going to deinstall. I unscrew that and go away, and I'll take this and we'll be gone in 5 minutes, which is compared to now rolling up the cable.
Thanks, great things again. So the last things for today is the energy efficiency part that Dario will show us, and we have Turin remotely connected. Yes, still working. Okay, please go.
Okay, so thank you very much. So today we are connected with my colleagues in Turin since we developed and installed the testbed prototype in Turin, connected to the mobile network, to the live commercial network in Telecom Italia mobile in Italy. So that's why we are connected with my colleagues that in a few minutes will present some demonstration. Just to give you let's say an introduction of what you will see. We hosted a prototype implemented and developed in collaboration with Capeti Elettronica, which is a sub-grantee of Telecom Italia in this task. And the goal was to build a prototype and develop innovative solutions for energy efficient management of LTE network with machine-to-machine services. You can see here the environment where we installed all the devices, and Gian Michele will present more in detail all the parts involved in the testbed. Just to give you, let's say, a few ideas of what is, let's say, the intention of this experimental activity. Of course, the testbed was a small-scale demonstrator, a small-scale prototype, but aiming to let's say, have, to be, let's say, representative of some use cases, like, for example, indoor condition monitoring, electric energy monitoring, focus on also on all the smart building services that are able to replicate the single environment testbed. So we focused our attention on selected area of improvement, like LTE commercial network in Italy, radio base stations, by optimizing the radio link, switching off some cells. We implemented a gateway for machine-to-machine infrastructure and used a wireless sensor network very efficient from the point of view of the power consumption. So here is the more or less the scheme where you can see all the devices, the LTE network, the gateway, and the wireless sensor network. I would like to emphasize the fact that we started from the LTE network because this is the focus for the operator to, let's say, improve the energy efficiency in terms of, let's say, electricity bill for the operator is very important. So we implemented some selective on-off switch policies on the LTE cell. And according to this strategy, we installed the wireless sensor network and the gateway by using sensors that are very efficient, but of course by concentrating our attention on the design of the gateway, because this is the essential part that is, let's say, the bridge between the capillary network and the LTE. You can see here a scheme of the prototype developed, and we focused our implementation on 3 phases, starting from an hardware, not yet, let's say, optimized, but we improved the firmware with the new energy efficiency features in order to improve the energy efficiency of the gateway itself. And then we implemented a second form factor in order to have a more compact device with better energy performances. So I hope now I see Gianmichele, my colleague, which is with the mute. So if you would like to unmute, because we cannot hear you, okay? So now the floor is yours. Thank you very much, Gianmichele. Thank you very much, Gianmichele. Please start with the demonstration. Okay.
Okay, I can start to describe the demo. Here we can see the sensor in the room. In this part, we have the gateway and the laptop, where we can see the sensor information, private information. And now the task of this test bed is to monitor the power consumed by the gateway. In the oscilloscope is connected to the gateway, and we can measure the power consumed in idle mode. Now with this key, I will trigger the transmission . Okay, I will trigger the transmission of the gateway to the node. Now we can see the transition from idle mode to connected, and the transmission power is increased. And this is the way we use it to monitoring the power consumption of the system.
Yes, and thank you very much, Gianmichele. The important thing
Dario,
here,
you can go on if you want.
yes, the important thing here is that we understood that when the cell is switched off during the night, the device is trying to connect many times, consuming a lot of energy. So we improved the firmware of the device in order to optimize the behavior according to the behavior of the electron itself. So we adapted the machine-to-machine service with the behavior of the LTE planned switch-off policy. So we achieved improvements in all the 2 parts. So of course, from the electricity bill is more important the base stations, but we wanted to, let's say, guarantee also the machine-to-machine service continuity. So we improved the energy efficiency of the LTE network. You can see here in the slide an important saving. And on the other hand, we guaranteed the service, the machine-to-machine services, and we also improved the energy efficiency itself of the gateway by 50%, which is impressive. Of course, in relative terms, not because this is important from the point of view of the electricity bill of the operator, but in order to guarantee the lifetime of the device itself. In fact, we have on one hand impact for mobile operator on the electricity bill. But we guaranteed the service continuity, and we reached a better efficiency of the gateway itself in order to, let's say, facilitate all the deployment problems that are usually important for installing a machine-to-machine service. Like, for example, 50% reduction photovoltaic module size, backup batteries, reduced overall weight and space occupancy, which are practical problems for the installations, and better installation characteristics, of course. And this result is also relevant in the view of future 5G systems, also because you see the trend is of, let's say, connections that are expected to grow with 45% of annual rate by 2019. So thank you very much, and thank you also to my colleagues connected in Turin. So I hope you appreciated the live demo. Thanks.